Welcome back. This is lecture 4, Introduction to Deep Learning. So last time we introduced you to perception. And when it comes to perception, we can't avoid learning deep learning. I mean, deep learning is the bread and butter for perception. So we will have to learn deep learning before we actually get into perception, technologies and techniques that are widely studied these days. So and some of you may already have some background in deep learning, but some may not. So I will start with introduction to deep learning, okay? Outline goes as follows. So I'm going to introduce you to 3 topics. The first one is deep feed-forward networks. Second is the convolutional networks, and then the transformer. So these are the essential key ingredients for computer vision deep learning. So I mean there are more, but these are like the main essential tools we have when it comes to deep learning for computer vision. So we'll quickly review these topics, and then we'll jump into more detailed networks that are used for perception algorithms. Oops. Deep feed-forward networks. Neural network model as a function approximator. Like we briefly mentioned last lecture, neural network model can be used to approximate a real world representation or function. And the objective is to approximate this model so that it reflects, it imitates the real world data. And this is the model that we need to sort of train and hopefully come up with. But what's unknown is this function. So we have this parametric mapping of y equals to f of x and theta, where x is the input and y is the output, and theta is the parameters. And we need to find these parameters through training process. And it's a composition of many nonlinear functions, which is the neurons. We need to determine the parameters theta using the training sample to get a good approximation to f star, which is the ideal function that we want to approximate. So when we have this type of deep feed-forward neural network, then we can, in general, we can describe the model as follows: y equals to f of x, which is also now a function of, so we have layer 1, 2, 3. Well, we have one more, but it's not shown here. But anyway, so it's a function of inputs. So let's talk a little bit more details about the network. So if we break down this neural network, there's this hidden unit. Each neuron, so this is the output unit, and these are called hidden units. And hidden units consist of these neurons, which is the nodes that you are looking at. And if you look at inside of this node, what's inside of it is pretty simple function, math function. So it's nothing more than a weighted sum. So we can which can be described as a linear function. And then you have this activation function, which maps input output of the linear function to the output of the neuron. So you have these inputs to the neuron, which is these inputs, and then you have weights. These are parameters we want to sort of find or optimize. And then we have this simple linear function that maps input to the output, and then output of this linear function is now mapped to the output of the neuron, which is now nonlinear. This nonlinearity is important. Let's take a look at this slide. So this slide shows the structure of the sample feed-forward neural network, and you are looking at three network with 3 hidden layers, and then 1 output layer, and the depth. So the depth is 4. So when we say a shallow network, then we mean this. There is this layer is small. When we say deep network, then we have many layers. And when it comes to parameter optimization, which we want to train, then we can describe this output as a function of x. And if you look at this function, then you can see that we actually we can break down each layer from the output side, from the input side or output side. So take a look at this part. So this part corresponds to the first hidden layer, and then this part corresponds to second hidden layer, and this part corresponds to third layer, and then we have the final output layer. And what this is saying is that the output of the hidden layer is described, can be mapped with this function f1, which is function of x and theta 1. And then now this becomes input to the function 2, which is the second layer. And then we obviously we also we need theta 2 parameter for the hidden layer, and then we can map input to the output using second layer function, and then it goes on. By doing this, we can have multi-layer network. That's where deep learning comes in. And before we move on, but what's interesting, what's important to note here is that these functions should be nonlinear functions. And if you go back to the slide, if you look at inside of this node, each node, then when you have this linear function, this is nothing more than vector and matrix multiplication. But what's important here is that we have this activation function that maps output of the linear function to the actual output of the neuron. And this activation function is what's making this neuron a nonlinear function. And that's important because let's assume that these functions were simply linear function. Let's say A, B, C matrix, which is this function. Let's say we did not have activation function. Then what's going to happen is that now y is going to be C, B, A, and then X, right? Assuming theta is determined, okay? Then what does this mean? What this means is we can actually make this another, turn this into another matrix, and this becomes linear function. So if you use linear functions only, then having this multi-layer is meaningless. Okay, so that's why this activation function is very important. Okay. So now let's move on to activation function. We have many types of activation functions, and actually deep learning actually really accelerated with the rise of introduction of value function. That made optimization problem quite easy in practice. I mean, deep learning requires all kinds of deep learning is a result of many things, such as big data, parallel computing power, chips and GPUs, and those hardwares are also required to compute these computing heavy optimization process, and also requires optimization software, and we also need these deep learning theory networks. So it became really powerful with all these technologies were realized, became available for researchers to, dive into this area. But one of the trigger that recent about 8 years ago was this ReLU function. By using this ReLU function, training process was really effective. It was much easier to train. But anyway, and let's take a look at why that was the case. So okay, let's start with linear function. So if you use this linear function, then it's non-existent, right? So you're just passing the signal, and now the neuron is linear function. But again, if, like I said, if it's linear function, then the approximation, capability or model capacity will be limited. Okay, so we need to introduce some non-linearity into this activation function, but it needs to be trainable, right? We'll talk more about what we mean by trainable, and what it means is we need to be able to compute derivatives. So people proposed functions, activation functions that are that we can compute derivatives, such as sigmoid tangent. So if you look at sigmoid, so this is a sigmoid function, and this is the hypertangent function. And if you take a look at their derivatives are continuous and smooth. Same goes with hypertangent, and that's because it can be described by these. It has nice property that it's differentiable, and some of the functions or features they offer is that they start from 0. So in the case of sigmoid, it starts from 0 and then finishes at 1 with with gradient changes over time as a function of the input, where the gradient is highest near 0. And if you also use hypertangent, then you also have similar properties, but you start from -1 to you end up you saturate at 1. So, and the gradient is highest around 0. And what this would do is that, over time, when you apply optimization process, it will try to push these values towards either this direction or this this direction, so that it's stabilized. The gradient is stabilized. That way, signal is either in the negative zone or positive zone. But with ReLU, it was different in a sense that ReLU, if you take a look at this ReLU function, ReLU is simply a linear function with rectifier rectified at 0, meaning that below 0, output of ReLU would be 0, but above 0, it's a simple linear function. So this is not ReLU is not differentiable at 0. Okay, so if you actually look at the derivatives of ReLU function, it's either 0 or 1, but there's this discontinuity at 0. So initially people actually tried other functions, similar functions that is smoother around 0, but it turns out it doesn't really help much. So, and sometimes perform worse sometimes. So anyway, I think what we can see, what we can learn from this is having derivative. What this activation function does is it activates the signal for positive values, but it deactivates for negative values. Okay, so it passes through the positive values to the forward direction, but not the negative ones. So that's what it promotes. Okay. And let's move on to output unit and loss function. So when it comes to output units, it needs to be coupled with loss function. Output unit, and they need to also be designed based on the task type of task or function that you are trying to approximate. And because output unit is coupled with loss function, we also need to think about the training, which means we need to look at the data sets. So they are now they are all coupled. So let's take a look at this slide. So training process. Determine the weights of DNN using the training data. Training data set is x1 to x1 t1 to xn to tn. And x1 is the input and tn is the target. And we want to optimize the weights using the negative log likelihood function, also known as cost entropy function. So the output, I'm not going to, go through information theory or the theory behind this function, but what this means is it's linked to the loss function. Okay. So that the model actually can approximate the data. Okay. And there are different tasks, such as binary classification, multi-class classification. Then there's a regression problem. So, binary classification is when you have true false or yes no type of binary classification problem, then you should use a sigmoid function and use this negative log likelihood function. And when you have multi-class classification, usually softmax is used, which allows you to normalize the distribution over each class throughout the whole entire class. And then for regression problem, we have a function that maps xn to yn, and we need to train w. And this would be negative log likelihood function in general form. Now let's talk about optimization process, which is the network training process. The objective is to find W star, which is optimal parameter set of parameters, and that what this is stating is that we want to find W set of weights that minimizes this cost J. Usually the parameter space is large dimension. It's nonlinear, non-convex problems, so it's hard to quite difficult to visualize or optimize using gradient methods. This is just a illustration of 2D optimization problem. For instance, we have x, y, and then z, and we want to minimize z in this case. But in many cases, it's many deep learning problems consist of many dimensions. So it's hard to visualize. But this is just to give you an idea of what the landscape of loss function looks like. But let's start with, but still, even if we can visualize, sometimes visualization really helps you to understand. So let's usually we try with 1 or 2 dimensional examples. Here we are looking at 1D example to explain the gradient descent method. What it does is we compute first order, which is a gradient, first order values of the cost or loss function, and then we apply iterative gradient descent algorithms to find local minimum of a differentiable function. Let's take a look at this illustration. So let's say we have this is relatively easy, simple example with a convex problem where we have minimum that's global and local. And when we have let's say the initial values were here, then how can we find W that approaches that approaches this optimal value, right? Here, x being w, y being j. Okay, so we want to find omega w star, but it's unknown, right? In fact, this landscape is unknown. That's the problem. That's you know, that's most of the case. That's the case for many engineering problems, optimization problems. So the problem is to find this W star without evaluating or without exploring the whole design space, because it can take forever. So we want to converge, we want to find omega star, W star within a reasonable time. And this can be quite challenging when you have, humongous parameter space to optimize. Here, so we need to first compute gradient of J, and if we start it here, then we will have negative gradient, and that gives you positive value because we have negative in front of it. And then we have this eta. That's later on you will see that this is an important hyperparameter for learning process, training process, because that determines how much you want to move and if you use large value, then you are going to end up, you can end up here. So this was omega initial, and the next value could be here. But if you decided to use small eta value, then you will move small step, and then you will end up here. And this could be now omega 1. So if you use, depending on that eta value, you could do this, or you could be doing this. Okay, but if you pick the good good value, then ideally you want to one shot, one kill, right? That would be ideal situation, but it's going to be very difficult, especially when things are non-convex, nonlinear optimization problems. So so this was initial value, and this would be the next value that we want to try. So this is how the gradient descent method moves each iteration. And you probably heard of backpropagation algorithm. And what this does is, when we deal with deep learning, we have many layers, right? So we need to solve these gradients for each layer. And solving gradient for each layer repeatedly will very computationally heavy. And there's a nice technique that called backpropagation algorithm that use the chain rule to reuse computing resources, meaning that once we compute the gradient from the output unit towards the end of the network, when we train parameters or optimize parameters, we can do in backpropagation manner, so that we can use gradients that we computed from the output, and then we can compute gradients for we can now compute gradients for the n-1 layer, and then n-2 layers, and then we can do this propagation in backwards. And that in mathematical form, it's described here, and I think it's if you spend some time, it should be pretty straightforward and clear. And now let's move on to stochastic gradient descent method, which is the widely used optimization method for deep learning. And let's see why that is the case. So if we use gradient descent method, the traditional gradient descent method, we need to compute gradient based on the whole training data set. If we have large number of training data, then weights will be updated every epoch, and convergence will be slow, and the gradient will be deterministic and easy to be stuck at bad local minima. For instance, let's go back here. So here the example was a very simple, easy case, but in reality, this is the case. So let's do 1D example. Okay. So in this case, we have many local minima, and if you use gradient method, it's highly likely that you fall into this local minimum. So you need some way to get outside of this local minimum. Explore new areas. Try something new. So the way to do that here is we can do it. We can do stochastic gradient descent method. So if you use stochastic gradient descent method, what it means is you use samples from the data. So it's stochastic in that sense. So selecting data is random. So one data may tell you it's optimal this direction. Another data may tell you it's going to be optimal to this direction. So selecting different data can tell you different directions, different optimization results when you compute gradients, because every sample contains different data input and outputs. So that's nice. So so if you use stochastic gradient descent, then you have this randomness that allows you to escape from these local minima, and try different explore different space in parameter space. But the gradient is noisy and random, but that's also bad. That can also be bad, because you want to converge to the global minimum, or at least local minimum that's close to global minimum. But if you have too much noise in your optimization process, you may not converge forever, because of the randomness. So what's used for deep learning in practice is that SGD with mini batch. So it's sort of hybrid between conventional gradient descent and SGD. So you do SGD, but with mini batch data. So you don't use full data set for every optimization training iteration index iteration process, but you use mini batch of data samples. That way, the noise is reduced, randomness is reduced, and you still have that stochastic nature of sampling data. So you have nice balance between, you may have nice balance between deterministic and stochastic gradient descent. So you're going to update the weight for every mini batch. So it's between gradient and SGD. So this is an illustration of full batch, complete gradient descent, mini batch gradient descent, and stochastic gradient descent. If you look at this example illustration, obviously, complete batch gradient descent is the fastest and way to go. But like I said, this example, these examples are quite simplified problems. So here you are looking at 2D optimization problem with very convex problem, meaning that you have nice elliptical space. Okay. But in reality, it's much more nonlinear, non-convex than this example. So gradient descent, can fall into local minima very easy and cannot escape from those local minima. Okay. All right. Let me stop here. And then let me continue in another video clip. Okay. All right. Let's continue with convolutional networks. So far we introduced you to basic deep learning fundamentals. And then now we are going to look at some of the key components, when it comes to perception or deep learning based perception models. The first one is obviously convolutional networks. Convolutional neural network is suitable for the data of 2D grid topology. So this is widely, almost always used for image processing backbone network. Extracts semantic spatial features from the image. And CNN models are used as a backbone network to extract features, and the CNN features are used to perform different complex tasks. This one illustrates the history, summary of how CNN-based backbone network has evolved over time. Initially, people were focusing on improving accuracy, performance. And then later on, people started to look at their efficiency, meaning that, we don't want too large backbone network for both real-time inference and computing efficiency. So usually we look at this region as utopia, lower computational load with higher performance. So you can see some of these networks are a good compromise between the speed and the performance. Let's take a look at history of CNN models. It all started with AlexNet in 2012. Initially, it started with 5 convolution layers, repeatedly apply 2D convolution using a sliding window, also called a kernel, and produce 2D spatial feature maps in a hierarchical manner. And 3 fully connected layers classify objects based on the spatial feature map. So this for image-based or computer vision domain, AI was basically starting from this network. It was a breakthrough. And let's take a look at how convolution operation is processed. So there are these key steps performed in each convolution layer. When you have inputs from previous layer, you take that input and then you go through 2D convolution operation, and then you go through nonlinear function, and then you go through pooling stage, and then you move on to the next layer. And this is how 2D convolution operation is done. So let's say you have an input of 5 by 5 matrix here, and then you have a kernel. And what you do is, as illustrated below here, you apply this kernel for you slide this kernel over this spatial over this image space. So you go through this sliding window type of convolutional operation. And by doing this, you compute basically each value of this reduced size of matrix. So initially you had 5 by 5, but now you have 3 by 3 matrix. So this does, so by using this kernel, you are sort of extracting feature, using the kernel, and then you are also reducing the size of the feature space. And for image case, you actually have 2D convolution with tensor structure, because usually when you're dealing with RGB camera, you have 3 channels. So you have image depth, usually is 3, and then you have actual the image space, which is image width and image height. So you have this kernel that's tensor, and you go through this sliding process to compute the output of the convolution operation. And then there's this hyperparameter called stride. So you could use stride, you could do convolution with stride equals to 1. Then you're basically sliding the window by one element by one element. Or you could actually stride faster with convolution with stride 2. Then you can skip one element. That way you can slide faster, and you will end up with reduced size of the output. So you can reduce the size of the the features much faster if you use these higher number of stride. But of course, if you do so, you may miss some features, by missing one stride. And then the last, usually the last operation is the pulling. Pulling, let's go over this description. Pulling reduces the spatial dimension of the feature maps by replacing the output of convolution layer with a summary statistic of the nearby outputs. So this is, let's say this is a feature. So this is the output of the convolution layer you applied, and you can further reduce the size of the matrix, and you can sort of extract more interesting, more important feature by applying this pooling operation. And you could do, there are different types of pooling. Often widely used pooling method would be max pooling, and then there's average pooling. So max pooling, sort of picks feature that's strongest, and you just remove all the other elements or features, and then you just keep that strong features. And by doing so, you can make this feature extraction more efficient, meaning that you can reduce the size of the feature space. And then there's average pooling. So if you do max pooling, then you may miss some information because you're just picking on value that's highest. But if you do average pooling, then you are considering, you're taking account for all elements. But then the problem may be things gets averaged, and you don't see this strong feature that may be important. So different combination can lead to the same value of average. So oftentimes max pooling is widely used. And also just like stride, when you do pooling, you can do overlapping and non-overlapping pooling. So it's very similar to the stride concepts. So you can do pooling without any overlapping elements, or you can do it with overlapping space. All right, let's so we looked at the low level components of the CNN operations, and let's look at the architecture, CNN models, how in history how it developed. And so let's start with VGG net 2014. VGG net made a deeper network, and used 3x3 convolution filters, and then used cascade of 2 3x3 convolution filters, and they find it yields better capacity. So capacity of the model means it can describe more complex features, and the model can describe more complicated functions, and smaller number of parameters than using a single 5x5 convolutional filters. So that was one key finding when they proposed this. So deeper gives you more capacity, better performance, and less parameters. People tried all kinds of different architectures. From Google, this is GoogleNet. They proposed this module called Inception module, and they tried different kernel size, 1x1, 3x3, 5x5, because different size of the filter may be necessary for finding different size of the features in the image. So, or you don't know, so we don't know whether 1x1 convolution would be more effective versus 3x3 or 5x5 convolutions when you're doing different computer vision tasks. Some object may be small, some object may be large, so they used a different size of this kernel sizes for a single layer. And then it turns out it helped. It definitely helped performance. And then later on, there's this network called ResNet 2016. People went quite crazy with this when it comes to this network architecture. So here, people tried very, very deep network, and people tried whether using 56 layer gives you better performance when compared to 20 layer network, because earlier studies found that deeper models gives you better performance, better capacity, and so forth. So they went crazy with this, and they used very, very extremely deep. They tried very deep models, but they found that the error did not improve when it becomes too deep, and they found that when you do training process, when you optimize these parameters using backprop, they found the gradient gets reduced. The gradient vanishes when the model is too deep. So to mitigate that problem, they propose this skip connection. Okay, so let's take a look at this a bit closer. So initially, this is what conventional network looked like, but then they proposed to introduce this skip connection. So you create a path that input can directly feed forward to the next layer. And what does this mean? So by doing this, this module now becomes so let's say this is h of x. Let's say this function is h of x, where x is the input. And if you introduce this skip connection, then what it means is you turned your function now into f of x plus x instead of h of x. So now f of x, which is not the same as h of x, but because you have this skip connection, what you need to learn would be this f of x, which is so the goal is to learn this residual. So the total function was h, but if you subtract x, then which is this part, which we need to learn parameters, that's going to be the f of x. By doing this, you can mitigate that vanishing gradient problem, because you have this backward path that you can pass the gradient directly, and then this layer only needs to handle this residual values. So so it's easier to learn, basically. easier to optimize. Okay. So, and this propagated this skip connection idea was now used by different applications, different computer vision tasks, and one application you're looking at is segmentation task here. So when you do semantic segmentation, your output needs to be pixel level classification, and so you need both encoder and decoder. Looks something like this, but initially, if you needed this part, deconvolution layer, and this is a convolution layer. So you create this feature extraction. So usually people call this backbone encoder, and then you have this decoder part, which depends on the task specific network. And in the case of semantic segmentation, you needed this deconvolution network. But if you take a look at this, there is a good symmetry between the encoder part and decoder part. And if you can actually use some of the skip connection idea, and you can pass on this information directly from encoder layer to decoder layer. So this is one way to draw this. Sometimes people call draw in this way too. So there are different ways of drawing it. Okay. So the point is, skip connection really helped to improve performance while making the network easier to train. Okay. So now skip connection is everywhere, and the model is usually very deep, used with small kernels. Okay. Let's move on to transformer. So I'm sure many of you have heard of transformer. In this class, I'm going to sort of summarize the main idea and the evolution or history of transformer. So it started from attention in the early stage, and then moved on to people use for self-attention, and then this block called transformer is now used in many applications. So what is transformer? It's a neural network with attentions. First proposed attention to process long sequences, currently used in many SOTA methods in various tasks. Let's start with attention. The idea is it scores the correspondence between sequence data. First added to RNN models for processing longer sequences, enabled to look at different parts of the input at each time step. To explain this more in detail accurately, I need to go through RNN, but this is not deep learning class, so I'm not going to get into that. But RNN had this problem of passing. When you have long sequences, there is this also sort of vanishing problem. If sequence is long, then you don't have sufficient feature from a very long something that happened in long history. So the performance wasn't great. And then this attention and transformer was a pretty big breakthrough in language models. And then it was also adopted for computer vision community. Let's look at attention. So let's look at this is RNN based conventional RNN encoder decoder sequence. It's called sequence to sequence. You have sequence, in this case sentence, and then you have output. This is a translator translating task. So when you put English as an input, English sentence as an input, and then you want Spanish as an output. I'm not sure what language this is, but anyway, this is a translator example. And the problem was that the RNN was sharing parameter in this manner. So when you have this network, this is all same network. So you put this input and then you process it, and then you output, and then you go through second input, and then you process, you go through the network, and then you output. So it was this is how the making the network scalable in terms of vector length or sequence length. In fact, if you go back to CNN models, so deep learning is all about making it scalable. So if you look at this for CNN, you basically need kernel or filter that can slide through the image space and then extract features, right? And the problem is that your image could be small, your image could be large, but you want to make your models scalable. So image can be different. Your object can be small. Your object could be large, and it must be able to handle these scalability. Size of the object and size of the image. So that's where this sort of sharing, parameter sharing, comes in, and using the kernel allows this scalability, or image size and object size scalability. If you come back here, and for sequence to sequence problems, language problems, the problem is that the length of the sequence is not fixed. Okay, the sentence could be short, the sentence could be long, so it must be able to handle different length. So an RNN was very good when it comes to scaling this length. It was suitable for sequence problems. So because it's sharing this parameter for the sequence. So that was the key idea of RNN. But then the problem was that you need to compute, you can only compute H4 after computing H3, H2, H1. So that was one of the problems. And another problem was that when you have this state vector, which is the output of the encoder, and you're going to use that information to decode. But the problem was that after, when you have long sequence, long sentence, you don't have good feature from this long sentence, because you have to go through this sequential network processing many times. So when you decode, for instance, you maybe need to focus on the first or second word when it comes to translating, or you can think of chatbot as well. But when you have this long sequence problems, the performance wasn't great. So what people proposed was using this attention idea. So you bring this state vector, and then you compare that with these hidden vectors, and compute these weights, attention weights, and then you can compute this context vector, which allows you to focus more on the features that are more important for this input. Okay, so that resolves some of the problems that existing RNN model could not provide. So by doing this, by repeating this process, your decoder can actually go back to your features that were in the encoder side, and then select or give more attention to features, hidden features that maybe in the early part of the sentence. So this resolved a lot of the problem, and then improved the language model substantially. And this is a visualization of what we just discussed. If you take a look at this, here it's English sentence. Here I think this is French. I'm not sure, but anyway, when it comes to translating, the word order can be different. So they must find the corresponding word or features to properly translate or decode from the features and context. So this was also used for computer vision community. One example could be image captioning problem. So they had to handle both image as well as language, because you want to describe the image using the language model. So you need both. CNN image backbone as well as language model as well. And people actually combine them and make this image captioning task work actually. And let's move on to the next slide, which is generalization of attention mechanism. So far we looked at the very early stage of birth of attention or transformer. And later on, people actually tried to generalize this idea and then proposed this attention module. And the way it's generalized is people proposed these three vectors. So the inputs would be query vector, and then you have another input that's so this is the input vector, and then you have query vector, and then you have attention weights. Okay, and then you take when it comes to deep learning, there's always this normalization necessary, because we're dealing with numerical values, and we need to be able to optimize and train these parameters. So oftentimes normalization is necessary in each layers. So you need softmax to be able to tell attention weights, and then you want to output these vectors, feature vectors, but then the way this is generalized is illustrated here. Okay, you have an input vector x1 through x3, and then you use that for two purposes. One is the key vector, and the other one is value vector. So the query, it literally was a query, which is the if you go back to the slide, this would be query, and then this would be inputs, and then these are attention weights, and then context is going to be the output. Okay, and then if you take a look, you have value vectors. So you have a value vector. So the way this works is using query vector and key vector, you find similarity, or sometimes error. Early stage, it was also called error function. And you compute basically attention based on these two vectors, and then you multiply that with value vector to actually compute the outputs. So here you can see that you actually need two inputs and one output. So this is a generalized attention mechanism, and the self-attention is that you have only one input vector. So when you have one input vector, you can use it for all three vectors, query and key and value vector, and you go through the same process. So you have attention, so similarity between key and query. So you find the attention, and then you use value vector so that you can compute the output using the attention weights, which is the result of the similarity matrix. So, and then computer vision community adopted some of these ideas for their image captioning problems. So your input is image, and then you go through the CNN backbone, and then use that feature as an input to the self-attention module. And you can generate, you can output, caption task. And transformer is a little more advanced and more generalized step after this self-attention. So as you can see, self-attention is here, and you use layer normalization, and you have multi-layer perceptron layer, and then you have another layer normalization layer. So this is called a transformer block. And by using multiple of these transformer blocks, language models made substantial performance improvement, and this model can do this is very suitable for parallel computation. Remember, the traditional RNN was a sequential process, so you had to go through this computing in sequence manner, but you can put input all together, and then you can get the output by using this parallel computing. Okay, so it's a highly scalable. So this was very good ingredient, a new block for language models, and this is also used adopted for many computer vision tasks as well. Okay, so let me wrap up here. Thank you for your attention, and let's move on to the next lecture. Okay.